Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks very much for the invitation. It's a pleasure to be here. I'm going to talk to you today about temporal variation of unknown characteristics, in particular with reference to streaming data analysis. So the motivation for this work is situations where a learning algorithm must operate in near real time online and be tolerant to unforeseen changes in the data generation procedure. So online learning has been very well studied already, but the tolerance to drift has not been so much studied so far. And that is a problem when it comes to real applications, because in most online settings, you do have situations where you can expect disturbances to occur in the system that you couldn't have predicted, and they can change the structure of the data and your target, your learning target. So examples of that are internet services. Recommender systems is very familiar to this audience, I'm sure. But also retail banking, where you detect fraudulent transactions and try to classify them as opposed to legal transactions. Financial data, audio, video, and environmental monitoring via sensor networks, where the situation that you're monitoring is too complex to be able to model in advance in full. So you can expect some changes in the data, in the distribution of the data, that you need to be able to handle on the fly. So this is collaborative work with my supervisors from Imperial College London, Professor David Hunt and Dr. Adams, my ex-supervisors, as well as David Leslie at Bristol University. There are other collaborators as well that I will mention as we proceed with the talk. So let me try to explain the point of view that I'm taking. So it is very common in streaming data analysis to select a tool that was designed for the offline case and adapt it so that it can work online. The most popular and simplest way to do that is simply by enforcing a sliding window. So you take your favorite algorithm and you apply it to a window of the last W observations you've seen and repeat that as you slide along in real time. So the pros of this approach is that it's online and drift tolerant in a very simple way. You don't need to make any changes to the algorithm itself. So the method of a sliding window is universally applicable, but it's obviously very naive, and that has its consequences. The obvious one is that it's very inefficient in terms of both computation and information, because at every tick of the clock, you need to recompute your estimate, your parameter estimate, your learning objective, given information that overlaps significantly with what you did before, and you're not exploiting that. And also it features a very unnatural sharp cutoff. If you only train your learning algorithm to the last W observations, then you're claiming that the observations up to W steps before are equally important, but one step even before that is not important at all, which is a very unnatural assumption. And the key question in these contexts is how to choose your window length. So even if you were able to recompute everything from scratch at every tick, given the last W observations, you would still have to choose the window size in an optimal way. So another way to adapt an offline tool to a streaming context is via the use of learning rates. So let's adopt for a second an offline learning theory perspective, where we have a loss function that measures how well we're doing. So we have a parameter theta that we're trying to estimate the value of, and we have a function that measures how well theta fits a data point x. That's our function L, the loss function. So we want to target the value of theta that minimizes the expected loss over our expectation of the data. So we want to have minimum loss on average, not for any given data point, but on average. But because we don't have access to the expectation, we don't know the true data distribution that underlies x, we use a sum as a proxy. So that's an additive loss function. A standard method is gradient descent, where at every iteration of gradient descent, we update our estimate of theta by moving in the direction of the gradient of our loss, which in this case is the sum of the empirical losses. This is an empirical loss itself, this sum, evaluated at our previous position. So this will converge eventually to the value that optimizes the empirical loss, the sum of the loss functions. So it will fit our data set as well as possible. But if we were working in an online context where data arrive continually over time, then at every time step, we would have to recompute, rather reevaluate this gradient at our new estimate, theta k. And this would involve measuring a quantity, computing a quantity for every data point from time 1 to time t. And that's not online. So a very simple way to turn this online is simply to move in the direction of the gradient of the goodness of fit of our estimate with respect to the last data point, xt only. And that's online gradient descent or stochastic gradient descent. So stochastic gradient descent does converge to the same value as offline gradient descent if you give it enough data and if you suitably tune the learning rate eta. Now it is clear from this expression that the learning rate controls the relative importance of novel information versus historical information. This is our historical information. Theta t minus 1 reflects our opinion about theta currently. And this is the novel information. This is how well our previous estimate fits the novel data point. So by holding eta to a fixed value, which is non-zero, we can have tracking properties in the algorithm. So the algorithm can be tracking changes in the data distribution because it continues to take into account novel information. Instead, vanishing learning rates would yield a convergence of this algorithm to the offline solution, to something that is approximately equal to the offline solution. So again, the question arises, how do we choose the learning rate in this context? Clearly, the learning rate controls how much we think things are different from the history, so we need to be able to control it, but it's a question that we're going to address in this talk. So yet another way to adapt, to produce temporal adaptivity in offline methods so that they can apply to streaming context is forgetting factors. So this is also a very popular approach, and it's easy to describe it again in the learning theory perspective. So consider replacing an additive loss where at time t plus 1, our loss function, our empirical loss function, is the sum of our loss function over the history 1 to t plus the loss at time t plus 1. They should say t plus 1. I'm sorry about that. And let's replace that with an exponentially weighted version, where the history is being downweighted by a forgetting factor lambda, which is strictly less than 1, at every time step. This expresses a belief that we think that the history is less relevant to our estimate right now than the present. So we're giving more weight to the present information than to the historical information. So again, if you fix lambda to be equal to 1, then you just recover your additive loss and you recover the offline solution. But for lambda equals 0, you discard entirely the data history. So clearly what you want is something in between where you still pay some attention to the history, but you pay even more attention to present information. So in situations where the additive loss can be optimized recursively, there is a relationship between forgetting factors and learning rates. We're going to see that later on. So another example is that I've been recently working on is prior sample sizes in Bayesian sequential learning. I know that many of you do work with Bayesian methods, especially with sparse problems. They tend to dominate. So I thought of also adding this example. So let's consider for a second Bayesian linear regression, where we're trying to regress a response y to a feature vector x linearly. So we think that y is equal to beta x plus some noise. And we model that in a Bayesian way, so we need to have priors on all our parameters. So our parameters in this case is beta, which is the regression coefficient vector, and sigma, which is our residual variance, how much we think that the response varies even when we've taken into account the covariate vector. So a common approach to do Bayesian linear regression is to have a normal inverse gamma prior on these parameters, and then conjugate updating yields you also a normal inverse gamma posterior over these parameters once you've seen a data point. So you can continue to do that recursively without needing to store the data history. Again, this is a non-line algorithm, therefore. If you have a look at the equations that control this recursive update, you see that there's a quantity which you can refer to as an effective sample size. That's mu n, which when you update after you've seen n data points, it becomes equal to its previous value plus n, which is the number of data points you've just updated by. So if you consider an online setting where up to now you have a belief about beta and sigma encoded by beta 0 and sigma 0, and your effective sample size at that point is mu 0, then if you see n more data points, this is the update you're going to get. So after that happens and you get to see even more data, your posterior now becomes a prior. And in Bayesian analysis, it's assumed that you do have some control over your prior. You're free to set its parameters as long as you have some reason for doing that. And your effective sample size is now a parameter of your prior when you see your next data point. So in principle, you could just set nu n back to its initial value, nu 0. In this way, as more data accumulate, you would still keep track of changes in the data distribution while remaining Bayesian as far as the update itself is concerned. So there's scope for adaptive learning even in Bayesian analysis. So what is really going on here? The question that I'm trying to address is that when you are enforced by the application itself to enable temporal adaptivity in an online algorithm, there are ways that you can do that. You can sort of hack an estimator into being temporally adaptive. But in all these ways that I've addressed, the same question arises. And that's how adaptive do we want to be? So how do we choose the sliding window size or the learning rate or the forgetting factor or the effective sample size? So the intuition that I'm trying to capture in my work is that this represents a bias variance trade-off. And that's very well known in certain simple cases, but I think it applies much more generally. So when you pay attention to the whole history, but in fact your data arise from a time-varying distribution, then you're going to have some bias because you're taking into account old information which is no longer relevant. However, if you pay attention to too few data points, then you have too much variance because you only have a little bit of information on which you base your estimation. So your estimates are much more volatile, and perhaps a trade-off between the two is possible to achieve. So in practice, what we need is online data-dependent methods for tuning these parameters. And a common solution is to optimize, again, the one-step-ahead loss. So you try to see how well you're doing with a given value of a window size, and then you update that value depending on your progress, so on how well you fit the t+1 data point. So an example is, for instance, at time t+1, you can run 3 updates for each of 3 choices of learning rates in a stochastic gradient descent. Your current value of learning rate, eta t, and one value that has incremented the learning rate by a little bit and decremented the learning rate by a little bit. Then you can select among them using one-step-ahead loss, which of your estimates that were produced by either one of these 3 values best fit the next data point. And then you set your learning rate to the learning rate that performed the best. So this is a very naive, very generic approach that works because it's using new information, but it's very sort of computationally expensive and unstable. So there are far more sophisticated choices that we'll discuss later. Please feel free to interrupt with any questions or anything that's unclear. So what is really going on in this temporally adaptive estimation problematic? So let's take a step back and consider what we would do if we try to model the time-varying distribution that generates the data. So let's consider parametric estimation, where we assume that our data arise from some given probability density function, f, that is controlled by a parameter vector, theta, but now this parameter is changing with time. So imagine a Gaussian distribution whose mean and variance are changing with time. So theta t in that case would be the mean and the variance of the Gaussian. So what we do essentially is that we relax the IID assumption that underlies normal likelihood methods and Bayesian methods in an offline static context. So we think that our data are distributed according to the same distribution but with different parameter values. So what assumptions are we willing to make about the process that drives the evolution of the parameters of the distribution? In Bayesian dynamic modeling, which is the current state of the art in tracking time-varying distributions, what you do is you assume a joint distribution on both the parameter vector and your data. So you usually enforce some Markov assumptions, which means that you think that the current parameter value theta t only depends on the previous parameter value theta t minus 1, or maybe a few further steps back, but not on the whole history. And then you just turn the handle on Bayesian inferential machinery and you produce an estimate, an optimal estimate of theta hat t. Whether or not you can compute that online is a different question. But in principle, if you model the evolution of theta t, then inference will provide you with an optimal estimate. Now you can approximate that, and then you can measure how well your approximation is doing, but you do have an optimal estimate that you're targeting. So I'm trying to move away from this framework towards a temporally adaptive estimation framework where we're unwilling to make specific assumptions about the distribution of, about the evolution of the parameters of the distribution. And this is because in practice, that actually holds true in certain applications where we don't have enough domain knowledge to express our beliefs about how the system may change. For instance, in recommender systems, you may expect that people's tastes change over time, but it would be really hard for you to specify a given explicit dynamic model of how these changes take place. So instead, the temporally adaptive framework models the practice where one produces a recursive estimator, an online estimator, by hacking his favorite offline estimator into an online form. We've described a few ways to do that. One is stochastic gradient descent, another one is sliding windows, and so on. And then we study that under very weak assumptions about the dynamics. So we're willing to assume that the dynamics are well behaved, so we're willing to assume some stationarity perhaps, or some local stationarity, but we don't want to explicitly describe how we think the system is changing. So what we're aiming at with this framework is to have a system that performs always reasonably, but never optimally. We can't hope to be optimal when we're not modeling the process itself. So the next part of the talk is concerned with stochastic approximation, which is a framework that underlies a lot of the methods that I've mentioned so far already. It's a very powerful way to turn offline algorithms into online temporally adaptive algorithms. And the most basic example of that is a very old algorithm called Robbins-Monro. So Robbins-Monro algorithm is a sequential algorithm that tries to find the root of a function f. So it tries to find a value theta that sets f to 0, basically. And it's trying to do that on the basis only of noisy evaluations of the function. So the way it works is that you simply update your current estimate theta t minus 1 with a new value, new evaluation of f of theta t minus 1. But you don't have access to the actual evaluation, you have access to a noisy version of it, and that's what you place in your estimate. So for vanishing learning rates, the learning rate has to vanish at a certain rate, you do get convergence. So you're able to locate the root of f under very generic assumptions about the noise that underlies this observation. And for a learning rate constant and above 0, so if we keep the learning rate bounded away from 0, then we have tracking. We can track a time-varying function whose root is changing positions over time. So let me give examples of this process. Let's go back to the stochastic gradient descent example that I mentioned in the beginning of the talk. So recall that for a loss function L that measures the goodness of fit of a parameter estimate theta to a data point x, we have this algorithm, this online algorithm, for determining the optimal value of theta. In fact, if we have a careful look at this algorithm, it is itself a Robbins-Monro scheme, because what it's trying to do, it's trying to set the gradient to 0, but it doesn't have access to the expected gradient itself. It has access only to noise evaluations of that gradient, and the noise here is produced A, by the fact that we only get to evaluate the gradient at one position xt, which is a noisy version of the average that we're trying to optimize, and B, because we're evaluating it at our previous value theta t minus 1, which is itself noisy. However, Robbins-Monro schemes are generic enough so that this type of noise is not a problem to it. It still converges to the optimal solution as more data arrive. So a very well-known example of that is list mean squares, which solves the same problem as Bayesian linear regression, but in a frequentist way. There's no priors. And in this case, our loss function is the squared residual error between our estimate of y and its actual value y. And you see that if you take the gradient of that, you get list mean squares, which is a well-known algorithm in adaptive filtering. But in fact, stochastic gradient descent is quite generic because you can substitute any loss function in there. Another example of a Robbins-Monro scheme, which I've been working on lately, is online expectation maximization. And I'm going to build up this algorithm from its very simplest case to its full version. So let's focus first on a simple average. Let's say we're trying to track the average of a data sequence, x1 to xt. So the normal average is just 1 over t times the sum of the data points, and then you can write that recursively as a convex combination of historical information plus the new information, xt. So this is just trivial algebra, this step. Now, if rather than tracking an average, you wanted to learn the maximum likelihood estimator of the parameter of an exponential family model, and exponential family models are a family of distributions that contain Gaussian, multinomial, Bernoulli, Poisson distributions. It's a very large family. It turns out that all you need to do is you switch to sufficient statistics of the data sequence, of the data stream. So there's a function S, a fixed, known, deterministic function that only depends on the probability distribution. And if you transform your data sequence via that function, then the empirical average of this transformed data stream is your maximum likelihood estimate of the probability distribution. So for instance, for Gaussians, your sufficient statistic function would turn xt, your observation, your multivariate vector that you observe at time t, at a larger vector that contains xt as well as xt times itself, transpose. The property of this sufficient statistic is that if you take the expected value under the true model, it recovers the parameter theta that drives your process. This means that this average here, this S of xt averaged over all time steps, is an estimate of your parameter in the normal way. In the same way as an empirical average is an estimate of the mean of x. So if one adds exponential forgetting to this equation, rather than forming a simple average, one forms an average where at each time step, the contribution of that data point is downweighed by a forgetting factor lambda. So what that yields is, again, a convex combination, an update that looks like a convex combination of historical information and present information. But this time, the weight that determines how much attention you pay to novel information is not 1 over t, as it was here, but rather it's 1 over nt, where nt is, again, something like a sample size. We call it effective sample size. And the effective sample size is updated by this equation here. Note again that for lambda equals 1, then this is the sample size. You just add 1 to it at every time step, and you keep track of how much data you've seen. And you recover the maximum likelihood offline estimator. But for lambda less than 1, strictly less than 1, you get some tracking properties because you downweigh historical information as you go. So, in fact, we can rewrite this in terms of a learning rate, because that's what this convex combination basically encodes, how much you're learning. And if we separate out historical information and novel information, rather, if we try to express our theta t as a correction to our previous estimate, so this is our previous estimate, theta t minus 1, and then we correct it by the discrepancy that we observe between the actual information and our estimate, then we get a Robbins-Monro scheme. Remember that a Robbins-Monro scheme aims to set a function to 0. It's trying to find the root of a function. And in this equation here, if that were 0 on average, then we would have our target, because the expected value of this sufficient statistic is the value that we're trying to learn. So moving one step further, this is where it gets more complicated, basically. Let's assume now that rather than observing the full covariate vector xt, we only observe a part of it. So for instance, we could have a multivariate vector that we're trying to learn the mean and covariance of. And rather than observing the full covariate vector, we only observe certain components of it. So what we would do in an offline setting is that we would probably use the expectation maximization algorithm. That algorithm is a very intuitive algorithm that says that all you need to do is you need to take the expectation of what is missing in your covariate vector, and that expectation you form using your previous parameter estimate. So whatever you think the parameters of your distribution are, this distribution with these parameter estimates gives you a way to form an opinion about what the missing stuff is. So if you iterate that, you fill in the missing values using your current belief about the system, and then you update your belief about the system by looking at the missing values, the imputed values and the actual observations. Then you eventually converge to the correct estimate of the parameters that drive the system. So in an online setting, what this would mean is that at time t, we would take our previous parameter estimate and then we would correct it by the discrepancy between that estimate and the expected value of the sufficient statistic, given what we've seen, and that expectation is taken under the distribution with the parameter estimates theta t minus 1. So this algorithm, again, is a Robbins-Monro scheme, and it still converges. So this is a very powerful framework. It allows you to do very intuitive things, and then it gives you a proof of the convergence using the same, basically, technique as the simplest case. So examples of this algorithm is Gaussians with missing data that I just described, and also mixture models, where what is missing in that case is the label of a feature vector. So mixture models is a way to cluster, basically, where you assume that there's a missing, never an unobserved label in every data point, and then you use expectation maximization to impute the best labels you can for each of the feature vectors. So one thing that is very interesting is that online expectation maximization can actually outperform offline expectation maximization in certain settings. It's commonly thought that online algorithms are an approximation to the offline solutions, but that's not necessarily true. In certain situations, online algorithms can outperform their offline counterparts, and this is because in this case, for instance, in the offline case where you get a bunch of data and you're allowed to revisit it as many times as you like, if you try to apply expectation maximization to this, the bottleneck you're going to get is not actually the data size itself, but the number of iterations that you've performed on your expectation maximization algorithm. So you're better off performing more iterations for a small bunch of the data first, so that you can save your computational power to perform less iterations of the algorithm using the whole batch of data. So this is the reason why online EM can actually sometimes outperform offline EM. So now we reach the point where we discuss how would we actually choose a value of the learning rate in practice. So all the methods that I've described to you so far point towards a general framework for online estimation that naturally features a learning rate, which controls how much we pay attention to novel information versus historical information. So usually the approach in online inference was to just let the learning rate vanish at a slow rate. Now that's not suitable for a context where we expect to have some temporal variation in the data generating distribution. Instead, what people did in the adaptive filtering literature at least was to employ a small fixed learning rate. So they would fix the learning rate at a constant above 0, and that would allow them to have some tracking. They wouldn't do as well as possible, but they didn't mind so much about that, because they thought that if eventually I reach a situation where my historical data is irrelevant, then this small learning rate will still let me update and adapt so that I can remain up to date. But it is clear from the argument that I described earlier about bias variance trade-off that time-varying learning rates can be preferable in certain contexts, and that the choice of value is very crucial for performance. Because if you're forgetting too little, if rather you remember too much of your data history, then you incur unnecessary bias. And vice versa, if you only pay attention to a very small bunch of data, then you incur unnecessary variance. Now, determining the optimal value via a theoretical argument, by assuming something about the way that the evolution of the system proceeds, kind of begs the question, because in my case, I'm not willing to make assumptions about how the system is changing in reality. Instead, I want a self-tuning method, really. I want a method that sees how well it's doing and adapts the learning rate to accommodate that. There's been a systematic study of self-tuning data-dependent methods for adaptive learning rates in least squares context, but not so much in more general contexts. And there's been various heuristics in streaming data analysis. So I'm trying to sort of consolidate these two fields and attempt to investigate which methods for adaptive learning rates work and which don't. So no one is really proposing that it's better to have a self-tuning learning rate method than an explicit dynamic model. But in situations where you cannot you don't have enough domain knowledge or computational power to have an explicit dynamic model, then it's good to know what works and what doesn't. So let me start by describing to you an intuition that can fail, but nevertheless it's very popular in the streaming data literature. So consider the following approach. Whenever your performance drops, then forget more. So this is a very common approach. For instance, in banking, in credit scoring, there's these scorecards that basically give a way to classify new customers as good risk or bad risk. And what they do with these scorecards is they train them on a big database of people, and then after a few years, when they see that the performance of the scorecards is no longer as good as it used to be, they retrain the system. So it's a very common approach to say that whenever your performance drops, just forget the data history, start anew. But this approach encodes a belief that says that the only reason why performance should drop is because things are different than what they used to be. And that's not necessarily true, in the following sense. First of all, there's a risk that you can forget too much by doing that. For instance, if you entirely reset the system and you start anew, then you're not necessarily doing the optimal thing, because maybe some of the information that you had before was relevant. So you don't want to discard all of it necessarily. So you may have over-dramatic reactions when you use that intuition. But another more subtle reason is that there are certain types of change for which forgetting more is not going to do any good for you. So there are certain types of change in a system that simply make your performance deteriorate, but that's not because your data is less relevant than it used to be. An example is in linear regression, for instance. You can have an increase in the residual variance of your response. And if that increases, you have nothing to gain by forgetting what you know about the linear relationship, because the linear relationship may still hold. So it's important to be able to forget more only insofar as that enables you to improve your performance. And that statement implies that we need some gradient information. We need to have information about the gradient of the loss with respect to the learning rate or the forgetting factor or the sliding window size. So the question is, can we get that information? So some recent work I've been doing was based on an approach that was initially proposed by Benveniste and Sutton in the adaptive filtering literature for least squares that tunes the learning rate online in accordance to an approximate gradient descent step. So it corrects its current learning rate by moving a little bit in the direction of the gradient of the loss function, of the one step ahead loss function with respect to the learning rate. Now, the gradient itself is not possible to compute online, because what that would mean is that you would have to rerun your whole algorithm from the onset of the stream, of the data stream, where you replace your learning rate eta t minus 1 that you've used previously with a new learning rate, a new candidate eta t. So it's a similar situation to the one we have with stochastic gradients, and in general, we cannot evaluate the gradient again from scratch, from the onset of the stream. Instead, what we do is we treat all the learning rates as instances of the same formal variable, eta, and then we differentiate with respect to that variable. And because differentiation is a linear operator, we can push back the differential through the recursions, and we can have an online approximate gradient. So the interpretation of this construction that Sutton proposed was that this is a derivative with respect to a very small change in the learning rate at all time steps. And this is exactly what we need, and it turns out that we can get that, we can compute that online. And let me show you a few examples of why this works better than the intuition that I proposed to you earlier, where you would just forget more if you observed any deterioration in performance. So what I'm plotting here is this gradient quantity computed on a stream that is tracking the mean and covariance of a 5-dimensional Gaussian distribution. Now, at time 1000, we observe an abrupt change in the system. So the data are no longer sampled from the same distribution as before, but from a different Gaussian distribution. Same dimension, but different mean, different covariance. In fact, in this case, I've constrained the change so that only one correlation between two covariates is changing. It changed sign at time equal 1000. So what we observe in the plot is the value of the gradient computed alongside an algorithm with fixed learning rates. In fact, I'm encoding this in terms of forgetting factors. So I fix my forgetting factor at a very high value, 0.99. that's very close to 1, so the algorithm is very close to being static. It's paying a lot of attention to the history. And you'll see that as soon as the change occurs, there's a very abrupt reaction of the gradient to that change. It suggests that you should forget more fast now because the system is very different. However, when we run the same algorithm and compute the gradient for lambda, for the forgetting factor fixed at a lower value, 0.96, where it's already forgetting more, the gradient reacts again, so it is spotting the change, it's detecting the change, but it's telling you you shouldn't forget that much more. You're already forgetting enough, but you need to forget a little bit more. So this is exactly what the idea is, that if you want to enforce temporal adaptivity in a system by playing around with its learning rate, then the optimal way to do it is to try and get some gradient information. You need some guide that tells you you should only forget more if that would lead to an improvement in performance. So here are some more extensive simulations with the same idea. So first we run our algorithm with self-tuning learning rate against a static context. What we see on the top plot is the learned forgetting factor. So the forgetting factor that the algorithm learns online by this self-tuning method that is based on the gradient. So in the static case, the thick blue line shows you an average over several experiments, and the two continuous thin lines show you the standard deviation around that estimate, and the dotted line is just a typical run of the algorithm. So you see that on average, what the algorithm does against static data is that it manages to adapt the forgetting factor to a value that's very close to 1, which is the value that you would optimally set for a static system. So it's doing the reasonable thing. This is kind of like a sanity check. It's doing the reasonable thing when the data are truly static. And this is the KL divergence between your estimate and the true parameter distribution. KL divergence is just a measure of discrepancy between two distributions. And you can see that eventually you do better and better and you stabilize. So you can also see that a typical run is volatile. It's not as stable as the average run, but it's not that volatile. It does stay within the bounds of the deviation from the average. Instead, when you introduce abrupt jumps to the system, every 300 ticks in this case, you can see that the forgetting factor reacts very rapidly to the change and also overcomes that change and then recovers very quickly. So that is the behavior that we would like to see. As soon as a change occurs, the system does reset to a certain extent. It doesn't reset entirely, which would be affected by a forgetting factor of 0, but it does forget quite a lot, and then it recovers. It sets the learning rate back to near its static value, which means that it's paying enough attention to the history from this point onwards. The same holds for faster change and also for smooth change. It's interesting to see that in smooth change, although on average you do learn a forgetting factor which is lower than 1, your typical run is quite volatile. So this algorithm is, one of its downsides is that it's not necessarily very stable. On average it does the right thing, but at any given run it will oscillate quite a lot. But still, this is very encouraging evidence that we can actually track the gradient on the fly. And this is for faster types of change. So if we only look at performance, then in the static case, for different values of the forgetting factor, ranging from 1, which corresponds to a static system, to 0.8, we see that the more we forget in a static system, the worse we do, because we incur unnecessary variance by not paying attention to the whole history. And the adaptive forgetting method manages to do nearly as well as the optimal forgetting factor of 1. Now, once we move to a system with abrupt changes, in this case, slow abrupt changes, then we see this smile type curve, which is exactly what the bias variance trade-off that I discussed earlier is referring to. So the optimal forgetting factor in this case is 0.98, and although it's quite obvious that for a forgetting factor of 1, which corresponds to a static system, we're not doing well at all, because we're paying attention to the history, which is becoming less and less relevant, what wasn't obvious so much in the literature is that you can also do worse by forgetting too much. So for instance, if you use a forgetting factor of 0.8, then you incur so much variance by not paying attention to enough information that you could have done a little bit better by remembering more of the history. And again, the adaptive forgetting manages to negotiate this trade-off automatically. Similarly, for faster change, although you see that the optimal value of forgetting is changing from a value of around 0.98 to a value of around 0.94, and similarly for smooth types of change. So to sketch the theoretical work that underlies this construct, rather than using an explicit dynamic model and comparing it to your estimate and discussing to what extent your estimate is optimal, in this case we use something called weak convergence of stochastic approximation theory. So weak convergence is something like a central limit theorem. We take the idea that our self-tuning method that controls the learning rate is itself a stochastic gradient descent, and we try to describe how that converges subject to the disturbances of the actual parameter estimate. The proof requires that the gradient process that I discussed earlier is itself stationary, and that kind of characterizes the applicability of this approximation. And that's a much more general assumption than the assumption that the process itself that generates the data is stationary or described by a Bayesian dynamic model. So I was thinking of now moving to some applications, and the two I had in mind is streaming classification via quadratic discriminant analysis with an example application to credit card fraud detection, and streaming clustering with mixture models. So streaming classification is a problem that has applications to various domains, real data domains. And the way we describe it here is that we consider a stream of labeled data where xi is our feature vector and ci is its label. And the assumptions are that the label of a data point arrives a little later than the feature vector, so there is use in predicting the label at this interval, but it arrives no later than the next feature vector, so that you may use the label, the true label, to update your system before you have to make a prediction for the next data point. Relaxing these regular sampling assumptions requires different arguments, but it's possible to some extent. But this is a good first approximation of what the system, of what streaming classification looks like in practice. So a streaming parametric classifier will have the structure below. It predicts the label of a given feature vector at time t using the current estimates of the parameters of the system, and then it uses the label itself, the true label CT that arrives a little bit later, to update its estimates. So it has two steps, a classify step and an update step. So our framework of stochastic approximation includes already several approaches to this problem. So you could have a logistic regression fit via stochastic gradient descent using a self-tuning adaptive learning rate, or you could have a perceptron with an adaptive learning rate. In this case, what we're looking at is a quadratic discriminant analysis classifier with an adaptive forgetting factor. So this algorithm has two steps as described, one classify step and one update step. In the classify step, it takes as input the feature vector xt and three sets of parameters. Now, the first set of parameter theta 0 is the parameter set that tracks the relative frequencies of the two classes. In this case, we consider two classes, but you can generalize it to any number of classes. So for instance, let's consider credit card fraud detection. Every transaction on a credit card has certain feature vectors, whether it was in an ATM, in a shop, the time, the place of the transaction, and so on. The class in this case is whether this transaction was fraudulent or legitimate. So we need to track the relative frequencies of the fraudulent and legal transactions, and that's tracked by the parameter vector theta 0. We model it as a Bernoulli trial with a given probability pt. And then we model the feature vectors themselves as Gaussians. And we model them as a different Gaussian, a Gaussian with a different parameter vector if they're legal than if they're fraudulent. So this is our theta 1 and theta 2, these parameter vectors. So at the classify step, we take we return the predicted label C tilde t that is given by the minimizing value between the two assumptions. Is this transaction fraudulent or is it legal? So this is a standard Bayesian decision theoretic framework. So to do that, we need to evaluate for each class. So we try out different values of class. Is it fraudulent or legitimate? And we evaluate the likelihood that this particular feature vector came from the Gaussian distribution that represents this class, J, and we also take into account the relative frequency of that class, P tilde J. So in the update step, what we need to do is we need to take our estimates of the parameters of the prior, the relative frequencies, and the two class conditional Gaussian densities, θ1 and θ2, and update them using the actual data that we observed. So we update the prior by the label, the true label, and the parameters of the distribution, of the class conditional distribution by the feature vector. So let's now see some results. We applied this quadratic discriminant analysis classifier with self-tuning forgetting to a real data set featuring 19 covariates and more than 500,000 instances. So we assume, and we make that happen via preprocessing, that the label is available with lag 1 exactly. This is not true in practice, because in practice you will learn whether a transaction was fraudulent or legal much later. But it is a good first approximation. And in order to measure the classification performance in this case, we use area under the rho curve, which is a performance measure that is robust to situations where the two frequencies are very different. So in our case, we observe many more legal transactions than fraudulent transactions. So you see that first I'd like you to look at this plot, which has the three forgetting factors. One for the prior, that's the red forgetting factor. This forgetting factor tracks how much the relative frequencies of fraudulent and legal transactions are changing. And then we have the forgetting factor associated to the two class conditionals. Lambda 1 is associated to the legal class, to the class of legal transactions, legitimate transactions, and lambda 2 is associated to the class of fraudulent transactions. Now you can see that lambda 2 is much more volatile than lambda 1. And that, we believe, comes from the fact that fraudsters change tactics much more often than legal users. So legal users tend to have similar behaviors over time, but fraudsters react to different regulatory initiatives. So you can see that the class of the fraudulent transactions is exhibiting much more dramatic change than the class of legal transactions. And here we compare to certain other methods. So the green line, which is on top, and in this measure, the higher the better, is quadratic discriminant analysis with the adaptive forgetting method that uses gradient information, this approximate gradient that I talked to you about earlier. So the black line, which you can see here, down here, is the same method, quadratic discriminant analysis, fits online, but with a forgetting factor of 1, which encodes our belief that the system is static. So you can see that that doesn't do as well as an adaptive forgetting method. So indeed, there's some value in forgetting in this case. But when we use two methods that use the heuristic that I talked to you earlier, that whenever your performance deteriorates, just forget a little bit more without using gradient information, then we do get performance that is slightly better than static. So, for instance, the blue line here is a perceptron that uses this heuristic, but we don't do as well as using gradient information. So, given that I only have a few more minutes, I may skip the clustering application and go straight to the conclusions and future work. So, to conclude, the take-home message of this work, I guess, is that stochastic approximation is a framework that encompasses a lot of techniques that are already very popular as a way to turn offline methods into online learning methods that are temporally adaptive. And that's because stochastic approximation naturally features a learning rate, and that parameter is an easy way to tune the algorithm so that it continues to keep track of novel information. So, for this reason, it's important and interesting to study the performance of these methods, the theoretical properties of these methods, and the extent to which we can optimally tune that parameter, the learning rate, online without relying on an explicit dynamic model. So, the conclusions from this work is that in adaptive forgetting, it's always better to have a bespoke approach, an approach that actually takes into account how this particular method depends on the novel information and depends on the learning rate, rather than having a one-size-fits-all approach where we have a sort of general recipe that says whenever you observe deteriorated performance, forget more. Moreover, adaptive forgetting is usually far more computationally efficient than a dynamic model, and it requires novel types of theoretical reasoning. And it's not necessarily easy to get right. Getting gradient information is not always that easy to obtain. And when you don't have gradient information, and the best you can do is just to forget more whenever you observe a deterioration in performance, you can get into vicious circles where you forget more than you should have, and because of that reason, your performance deteriorates even more, and then you keep on resetting and resetting without actually managing to track the system. So in terms of future work, some practical concerns are to handle the irregular sampling frequency that is observed in real data, and to handle delayed information. And that would be very important, for instance, in fraudulent transactions as well, because you usually observe the label of a transaction much later, even 6 months later than the actual transaction was observed. In terms of theoretical concerns, my main concern is to manage and show which of the methods for self-tuning learning rates actually works in this weak sense that I've described, and which one doesn't. And that requires understanding the assumptions of the proofs, the convergence proofs that underlie these stochastic approximation ideas, and to what extent these assumptions that are often quite technical relate to things that we can associate with the real world and real data. And I guess my current understanding of learning rates and forgetting factors is a way to do robust learning, but not with respect to departures from our model distribution, but rather with respect to our to departures from our beliefs about how the system is changing over time. So these are ways to have robustness to model misspecification about the dynamics of the system. It's interesting to observe that in certain simple cases, there are close relationships to state space modeling. So what you're doing by by adapting online your learning rate is actually very similar to a Bayesian dynamic model in certain cases. So that's also an interesting direction. And the adaptive prior selection that I talked to you earlier in sequential Bayes is also something I've been looking at. And finally, so far, this whole talk was concerned with parametric inference, where you have one parameter that you're trying to estimate the value of. But in non-parametrics, where the dimension of your parameter set increases with the number of data, some use of a sliding window is inevitable. And then you get into a situation where you need to remember not necessarily the most recent data points, but the most important data points. And that's very similar to active sampling, and also something that I've been working on lately. So this is my website. For more information, please feel free to visit. And any questions? Thanks very much.
Let's thank Chris. Any questions? I have a question.
Sure.
So, you gave the example of linear regression, right?
Yep.
Where you're trying to learn the linear relationship between X and Y. Now, suppose it was not linear, but it was quadratic. What would happen is that you would just change the slope of the function that you are basically predicting.
Mm-hmm.
But really, what you need to do is find out that the model is not linear, but it's quadratic.
Mm-hmm.
And that sort of does not happen in this
Mm-hmm.
framework. So do you have any thoughts of actually reasoning about the model complexity, that this is not
Mm-hmm.
probably the right model if you need to forget it a lot,
Mm.
right?
That's a very good question, actually. We're looking into that right now because we, in collaboration with Nikos Pavlidis from the University of Lancaster, we're working on a neural network, adaptive neural network. And there the trade-off is, like you say, that often when you look at the data in batch, they have a very strong quadratic or even worse shape. But then if you process them one by one, they're locally linear. So if you keep on forgetting, that could be because the distribution is changing, or it could be because you're just observing parts of a different distribution. So you can also use one step ahead error to tune model complexity. And then you get two parameters, one that controls the model complexity and one that controls the forgetting. And these parameters interact in very interesting ways. So sometimes it's very hard to tell the difference between these two, between poor fit because of bad modeling or poor fit because of temporal variation. But in our experience, it's possible to do better than not to worry about it, if you see what I mean. So
The other question I had was in terms of the computation of the sufficient statistics.
Yep.
For instance, if you have this linear fit, you can forget about most of the samples in your current window, but over the long term, you do not need to consider all the samples, but just some sort of sufficient statistic which basically say the mean was
That's right.
progressing in this
That's right.
curve-like fashion. only few samples,
Yeah.
which later on can be used for non-complexity calculation rather than the whole data set.
Yeah. So I guess there's maybe two points to address in what you said, in what you asked about. One is
One relates to active sampling in some sense.
that's right. Yeah. So one thing to worry about is that sometimes some of the sufficient statistics are changing in different ways than others. Now, if you have a different forgetting factor for each one, you could use that forgetting factor, its average value, as an indication of how much the system is changing with respect to each aspect. But then you start becoming a bit too ad hoc. So if you start introducing forgetting factors at the level of the data rather than at the level of the loss function, there's a risk that you may be just creating classifiers or creating estimators. You see what I mean? Because you can manipulate the data in too fine a way.
Yeah, but that is where priors come in, right? You need like prior models of complexity and what.
That's right.
What could be considered a feature and what is like overfitting.
That's right. That's also very true. Another way that you could, another point with respect to your question is that, in fact, this forgetting factor approach is non-parametric because for each time step you get a different value of the sufficient statistic. So it's interesting to relate the forgetting factor back to a dynamic model and then have at the end of the day, you can say that my mean had a variance, a temporal evolution variance of so and so, and then the variance. Yeah, so it's possible to do things like that. Yeah, very interesting. Yeah.